Ooh, yo guys, what is up? Welcome back to another video. Had a little long morning. Had to get some chores done, clean my apartment, do some things. So happy I got that all done. Made some food and ready to make a video now. So yeah, let's go straight into it. I believe this is episode 116 today. Looks like we got a horsey today. Let's check out the sound.
But right now, Horsey is the cutest Pokemon of all. Come on, Horsey!
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 Say that again. Horsey!
Horsey!
Horsey! Horsey! There we go. Horsey! What a sound. Let's go. But yeah. There's that sound. Let's jump straight into some problems today. Thinking back to about 7 days ago. I think it was about 7 days ago when I recorded, I think, the last 2-hour video that we had. It's been a little while. So, had a good break. Use smart list. Study plan. Let's do what should we do today? Trying to think. Are we still TTP? Ugh. Longest common subsequence. I think we looked at this one. We did look at that one. Best time to buy and sell stock with cooldown. Let's check out target sum. Have we done that one? No, we have not. About 50% acceptance rate. You're given an integer array of nums and an integer target. You want to build an expression out of nums by adding one of the symbols plus and minus before each integer in nums and then concatenate all the integers. For example, if nums 2, 1, you can add plus before 2 and a minus before 1 and concatenate them to build the expression plus 2 minus 1. Turn the number of different expressions that you can build which values to target. Okay. I was thinking backtracking. I'm trying to think. How can we solve this problem? Man, tough problem. Oh, I thought we'd do it for each one. You got minus here. Okay. Given an integer array nums and an integer target, you want an expression. Build the expression. This one here can only be minus 1, 1. Solving brainless puzzles. Okay. So I'm thinking So maybe we'd have to make some sort of like backtracking function, right? With an I and a cur, right? And now I and cur would be 0 for the index 0, and then cur would be, I guess, just an empty array, right? Our base case would be, well, I think let's do, well, if the length of cur is equal to the length of nums, right? So I think we have to build all of them. Let's do. Then I was thinking put an and here. And then we. I guess technically, I think I has to be at the end of this array, right? So. Then we would return. And then increase our count by 1. Right? Because we're returning an integer. So we make a count variable here. Cur.append nums I, right? Then we would have to do, well, we'd have to backtrack and do I plus 1 and pass in our cur. Otherwise, we'd have to pop and then do cur.append. Is it going to be prefix sum as well? How do we append negative nums I? I actually don't know. And then we would backtrack I plus 1 cur. Let's do and I is greater than or equal to the length of cur. Okay. Then here we'd have to check, well, we have to do some, let's do like sum cur is equal to the sum of cur. And we would compare, well, if sum cur is equal to target, then we would increase this count by 1 and return. Return our count. Oh my god, submit. Definitely not gonna submit, bro. On local count. List index is out of range. Well, I think it's because we're appending I plus 1, but there is no I. So there's something wrong with my base case here. I know for sure, but I'm actually not really 100% sure. Such a better way to do it, dude. Oh my god, man. Total minus nums I. That's why I was thinking prefix sum earlier, but total plus nums I, right? Backtrack. Well, this now needs to be a 0. It's now total. Non-local count. Let me check. Okay, well, yep. If the length of I. Okay, wait, now we have to do, well, if I is equal to the length of nums, then we have to check, well, okay, if total is equal to count is equal to target, we increase the count, then we return. We need IDP to this, so time limit exceeded. So now, how we IDP to this? I don't understand why this is a 2DP problem though. That's the thing. how we add DP to this. So we've got a total here, right? So I guess what we can match, we could use some sort of like hash map, right? A dictionary is equal to this, right? We can do, well, okay, so let's change this to this, right? So we would use I as a key and then total as a count, right? So we do, okay, well, if I total, in Memo, we would want to return dic I total. Yeah. Computer memorize. Plus is equal to backtrack I plus 1 total plus minus is equal to backtrack I plus 1 total. Why don't we do plus minus? Oh, okay. So they're saying we do a plus is equal to this, a minus is equal to this, right? But now instead, when we enter this base case here, okay, so we check if I is equal to nums, then we do, okay, well, if total is equal to target, turn 1 else 0. Okay, we get this, we get this, right? So then we're gonna need to do, okay, well, Memo, I total is equal to plus minus, right? Because when you get from this, you're either gonna return 1 or you're gonna return 0 each time, right? And then we would want to return Memo I total. Should be return 1 if total is equal to target else 0. Expected 0. count, base case. I guess we wouldn't need this, right? That's why. Always returning something that's 0. We want to return this. Non-local. Let's get rid of the count. There we go. Let's take a look at the video. Sorry, I've been a little quiet. I've been trying to focus a little bit. Take a look at this video. It's only 12-minute videos. So.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem target sum. We're given an array of integers called nums, and we're also given a single integer called target. And basically for every single number in the array nums, we can either choose to add that number or subtract that number. And we must do that for every single number. We have to either choose to add it or subtract it. And then using that, we will have some total or some sum at the end of our computation. And basically, we want to know, does that computation, that sum that we have, that total, is it equal to the target value that we were given at the beginning, right? And not only that, but we want to count the number of ways that we can get a sum from this array nums that will equal this target value. And then we want to return how many ways we were able to do that. So in this example, you can see we're given an array nums of 5 consecutive ones and a target value of 3. And you can see all the different ways that we can sum up to that total value of 3. There are 5 different ways to do that, right? You can see the first one. If we subtract the first one, add the next one, add the next one, add the next one, and add the next one, we're able to get to 3, right? Basically 4 positive and 1 negative, that will give us a sum of 3. You can see that the next example, the next way that we were able to do that, basically we subtracted the second one, added the first, and then added the next 3. The main thing though to note is that the order that you do these does matter. So if we can change the order of the plus and minus symbols, that counts as a different way that we were able to total up to the target. Right, so basically we're counting permutations. So this can be a complex problem if you're not familiar with it. So let's start off with the brute force solution, which is going to be 2 to the power of n, and then let's see how we can actually optimize that into a more efficient solution. So suppose we're given that same example that we just talked about, target of 3 and 5 ones in the input. Remember, for every single one of the values, we have a choice, right? We can either add it or subtract it, right? And the best way to visualize this for me is always using a decision tree, right? So if we want to know all possible ways we could, enumerate this, and all possible totals we could get from this array, a decision tree is the most helpful. Initially, we start at the index, right? We're keeping track of what index we're at, right? Initially, we're going to be at the 0th index. We're going to keep moving on and on as we make choices, right? To the 2nd, 3rd, 4th index until we, of course, reach the end of the array. Another thing we're going to be keeping track of, what is our total so far, right? Of course, we want to know what our total is so far, because by the time we reach the end of the array, we want to know, is our total equal to the target value or not? So using this pair of values as our parameter to our recursive function, we'll get a decision tree that looks something like this. Initially, we'll be at 0, 0, right? Index 0. And our total will initially be set to 0. We can make a choice, right? We're at this 1 over here, right, at the top left. We can either make a choice to add that 1, right, plus 1, or minus 1. If we add the 1, then our index is going to be at 1 because we're going to move to the next position, right? We're going to be at this position now, which is at index 1. And our total, right, the second value we're keeping track of is also going to be 1 because we added a 1. Now, if we did the opposite choice, we would still end up at index 1, but our total would be negative 1, right? That's our second value over here. And this decision tree is actually going to be pretty simple for us because all of the values in the input are 1. So basically every single decision is going to look exactly like this one. Let me just kind of quickly draw it out to give you an idea. Okay, so we kind of ran out of room, so I won't draw out the entire tree, but just to show you a path, a single path that will lead us to the target. So initially we start at the first spot, right? We add the first one, right? So this is a positive, right? We're at 1 so far. Then we go down this path where we minus 1, right? Then our total is at 0, so minus 1. Then we add 1 again. We're at index 3, total of 1, so plus 1 here. Then we add another 1. We're at index 4, total of 2. And then we add a last one, right? The 5th one, we add this as well. That leaves our total exactly at 3, which is good. And it puts us at index 5. Well, index 0 is here, 1 here, 2 here, 3, 4, 5 is exactly out of bounds. So as soon as we go out of bounds, we're done, right? We've reached our base case. Now we want to know, is our total so far, which right now happens to be 3, is it equal to the target? Yes, it's exactly equal to the target. So now we're done. We found a single way that we could reach the target value, right? Of course, there's going to be other paths in our decision tree that also lead to the result. But there's also going to be some paths that maybe sum up to, possibly 1, right? If we subtract 2 of them and then add 3 of them, that'll leave us with a positive 1, which is not equal to our target. So in that case, we won't count that. But ultimately, we're going to count how many different paths were able to lead us to that target value. Now, this is the brute force. Of course, this tree could have a height of n, and we obviously have 2 branches each time, right? 2 different paths for every single node. So that will put the time complexity at 2 to the power of n. How can we optimize this? Well, the trick is going to be in the parameters that we're passing into our recursive function, right? The index, which we're maintaining, and the total sum that we have as well. Using these, we can actually optimize this solution. So we can use the idea of caching to optimize this problem, as with most dynamic programming problems. So take a look at the parameters. We have the index, which we're passing in, and the total. Now, how many possible values could we pass in for the index value? Of course, the size of nums, right? So that's how many, n is how many possibilities we could have for this index. How many different possible values could we pass in for the total? That's definitely a little bit harder to determine. And the simple solution to that is, what's the maximum total that we could have from this array of nums? In this case, just add up all the nums. It's 5, right? 5 is the biggest number we could pass in for total. And since 5 is the biggest number, we could possibly also, if we subtract every value, we could get, pass in a -5 here, right? And potentially every value in between +5 and -5. Not necessarily though, but possibly. That's the big idea here, right? Since we're going for worst case time complexity, which is big O time complexity, we have to think about the worst case, and possibly we could pass in every value between +5 and -5. So overall, the way to think about how many different values we could pass in for the total is basically the total sum of the nums array, right? And let's just call that T for simplicity. So T, n times T, where T is the total number of values we could pass in, or rather the sum of the entire array. That's going to be the overall time complexity if we perform caching using this pair of values. So it's pretty easy to implement caching once you have coded up the recursive solution. So we can now jump into the code. Okay, so now let's write the code. It's actually not too bad. So remember, we are going to be using a cache. I'm going to call that DP. It's just going to be a hash map in this case. We in the number, right? In this just like a pair of values, this index total. And how are we going to do that? We're going to, of course, call our recursive function backtrack. And remember, we really had two choices that we could make. One choice was to add the value at index +1, but this for the plus, subtracting it, we go and be take how target result. Good to go. Base case, pretty soon, I always run it. And so I really hope the code works.
1 second, guys. Ugh. Okay. Looked at that one. Is it tough, bro? Maybe we take a look at some of the advanced graphs. Prims, Dijkstra's prims, Kruskal's topological sort. Here when we have graphs, it's just matrix BFS, adjacency list, matrix DFS, intro to graphs. Let's take a look. Advanced graphs, man. Jeez. Network. Delay time. I'm going to have to study all these algorithms again. I remember learning them, but you're given network event nodes labeled from 1 to n. You're also given times, a list of travel times as directed edges. UI, VI, WI, where UI is the second source node, VI is a target node, and WI is the time it takes to get from a signal to travel from source to target. UI. Okay. Travel times directed edge times I is UI. UI is a source node. VI is a target node, and WI is the time it takes for the signal to travel from source to target. We will send a signal from a given node K, return the minimum time it takes for all the n nodes to receive the signal. If it is impossible for all the n nodes to receive the signal, return -1. So we start at 2. We go to 1. That takes 1 second. We start at 2. Go to 3. That takes 1 second. Then we go from 3 to 4. That takes 1 second. We have 4 nodes. K is equal to 2. What is K in this case again? Okay, K is 2. So I think that goes to this node. And we have 4 nodes. Return the minimum time it takes for all the end nodes to receive the signal. The minimum time, well, the minimum time would be 2, 2, right? It was starting at 2. Okay, Dijikra's algorithm. I have to relook at this. Like, it's widely used for finding the shortest paths from a starting node to source to all other nodes in a weighted graph. It's particularly useful when edge weights are non-negative. The algorithm intuitively explores the graph, finding the shortest distance from the source to each reachable node. Okay. Prim's algorithm. Prim's algorithm is a greedy algorithm used to find the minimum spanning tree of a connected, undirected graph. And what's Kruskal's? I learned all of these. Kruskal's algorithm is a greedy algorithm used to find the minimum spanning tree of a connected, weighted, undirected graph. Prim's algorithm is a connected, undirected graph, is a connected, weighted. And then topological sort. Okay. So this one, oh shit. This one here, I believe, would be Dijikra's, which finds the shortest path from a given node. Right? You could use Dijikra's algorithm. Damn, bro, this guy's got a lot of problem solved. Damn, bro. Okay, let's watch the video on this. Network delay time.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve network delay time. The reason I'm solving this problem is because it's a rare problem that you actually have to use Dijikstra's however you pronounce that name, this algorithm. It's the shortest path algorithm. It's not super common on Leetcode, but I think it's a really cool problem to solve, a cool algorithm to implement. So obviously this is a graph problem. We're given a network of n nodes labeled from 1 to n. And we're also given a list of times. The times are going to be our edges. So it's going to be directed edges. So a time is a triple value. The first value in this triple is going to be the source node. So for example, this node 2, the second value is going to be the target node. So for example, 1 is this node. And the reason it's a target is we can see that there is an outgoing edge going from 2 to the 1. So every edge is going to be directed, right? We can see there's a directed edge there, a directed edge here. The third value, and this is also pretty important for this algorithm, is the weight of the edge. In the context of this problem, the 1 basically just means the amount of time it's going to take for us to go from here to this node, right? But this is the weight of the edge. So we're given a original node K. So this is our starting point. The node K is going to be the starting point. So for example, in this problem, in this graph, we're given k equals 2. That means this is the starting point for us. What we want to do in this problem is, starting at 2, how long would it take for us to visit every single node? Basically, if we sent a signal from here in every direction, so in this direction and in this direction, how long would it take for that signal to reach every single node? Now, if it's not possible, for example, in this case, it is possible, but what if we had a 5th node over here that's just not connected to these 4 nodes over here? Then it would be impossible for this node to send a signal here. In that case, we're simply going to return -1 because it's not possible. But what about in this problem? Because it is possible. How long is it going to take? That's the only question. Now, looking at the picture, it's pretty obvious. So starting at 2, how long is it going to take for this to reach a signal? It's going to take 1, right? Because the weight of the edge is 1. How long is it going to take for this node to get the signal? Also 1, because the weight of the edge is 1. So now we're over here. Let me just change the color to make it a little bit better. By the way, this was the original node. How long did it take this node to get the signal? Technically 0, right? Because it's the one sending the signal. How long did it take this 3 to reach the signal? 1. How long did it take this to reach the signal? 1. Now we're going to continue going. From this 3, we know that this 1 doesn't have any more nodes that it can send the signal to, but this 3 does. It has a node over here, 4, right? Now, how long is it going to take this 4 to reach the signal? Well, the weight of the edge is 1. So does that mean it's going to take the 4 1 second or whatever our time unit is to reach this? No, because we have to add the 1 from over here, right? Remember, our signal first started over here, then it traveled over here with 1, then it's going to travel again over here with 1. So in total, once we have visited this node, it's going to have taken 2 units of time to reach it. Now, after this node gets the signal, that means everybody has gotten the signal. How long did it take? What's the largest value we have? It took this one, right? This one took 2 seconds or whatever. So therefore, we're going to return 2 because after 2 units of time, every node has received the signal, so our output value in this case is going to be 2. Now, from looking at this example that we ran through, you might be able to tell that Dijikstra's algorithm is actually a breadth-first search algorithm that I'm going to show you the general idea of. But the one difference about regular breadth-first search is this algorithm actually uses a minimum heap, aka a priority queue. So we're going to be needing this data structure. It's not a super common data structure, but it is needed for this graph algorithm. Let me show you the actual algorithm. After that, we're going to jump into the code. So in case you want to Google this algorithm or do some more research, it is called Dijikstra's algorithm. It is a shortest path graph algorithm, and it's pretty common. You have probably learned it in school if you study CS. And what it does is, in this case, let's say our source or our starting point is this node, the value 1. What it does is for every other node, it basically tells you the shortest path, right? So for example, 3, what's the length of the shortest path to this node? Well, directly from 1 to 3, it takes 1. So 1 is going to be the shortest path for this node. What about this 2 node? What's the shortest path to this node, right? With this, it's pretty obvious because there's only one way to get here anyway, but take a look at this node. There's 2 different ways to get there. Now, is this the shortest path? It's the obvious path, right? It's just 1 node away, but the edge has a weight of 4. That's a problem because take a look at the second path that we can do. We can go to 3, right, over here. Then we can go to the 4, and then we can get to the 2, right? That took 3 edges, didn't it? That took 1 edge, 2 edge, 3 edges. But when we total these values up, we get a sum of 3. That means this path is actually shorter than the path up here. So it's not always clear, right? That's why we need an algorithm. And that's exactly what we have. We have Dijikstra's algorithm. And we're going to be doing a breadth first search, right? So starting at this node, the start node 1, we're only going to be possibly visiting nodes that are right next to our frontier, right? Depth first search would be we just go one direction and we just keep going, right? But breadth first search is we're going to do this layer by layer, right? We're going to go to the first layer, the next layer, and so on if we had a bigger graph, right? That's how breadth first search works. And every node that is on our frontier, right? So if this is our starting point, we have 2 options of nodes we can visit, this node or this node. These both are going to be added to our min heap, and we're only going to visit the one with a shorter path. That does make sense so far, doesn't it? It makes sense that we would want to visit this node because it has a shorter path rather than visiting this node first, which has a longer path, right? That makes sense so far. That's why we're using a minimum heap. Minimum heaps can get us the minimum value pretty efficiently, right? Every time we want to get a minimum value from the min heap, it's just a log n operation. Okay, so the way we initialize this algorithm is we know that we're starting here, right? What we're going to actually do is add this node to our min heap initially, right? So, and in our min heap, we're going to be keeping track of 2 values, obviously the path length, right? Because we're always going to be popping from the min heap based on the minimum path, right? So that's that's like our key value. That's what we actually care about, right? That's what's going to determine which one we pop, but we also want to keep track of which node it is, right? So initially the path to reach the initial node 1 is 0, right? Because that's where we're starting. So it doesn't cost us anything to get there. And the node itself is obviously 1. So this is how we're going to start. Then we're going to pop this value. It's only 1 value so far, so it's simple of where we're popping, right? Once we pop this value, what's our next step? Well, like I said, this is a breadth first search, right? So we're going to take a look at the node over here. It's 1. We're going to look at all of its neighbors, right? It has 2 neighbors, right? We're checking that first layer. We're going layer by layer with breadth first search, right? So this is our first layer, right? We're going to take the first neighbor, 3. How long does it take to reach 3? 1. We're not visiting it yet. We're simply adding it to our min heap. So the path length is 1, and this is for node 3. The other node that we can reach is 2. The path length is 4. Let's add that as well. 4, and the node is 2. And since we've already visited the node 1, we can cross it out now. So now we're popping another value. This time we have 2 values, so which one are we going to pop? Well, this is a min heap, right? We're going to pop the value with the minimum path. It's this one, right? Of course, that's the one with the shortest path. That's what we're going to pop now. So as we pop every element, we're basically determining the minimum path. So now we can say for sure that the minimum path to reach 3 takes us 1, right? Because 1 was the value that we added to our min heap. And again, we're just doing a breadth first search. What are all of the nodes that 3 has neighbors with? It only has neighbors with 1 node, right? This 4, we have a directed edge going exactly to 4. So let's add 4 to our min heap. So we're adding the node 4, right? So that's what we're going to put in the node position. What are we going to put in the path position? Are we just going to put 1 because it only takes 1 for us to get there from 3? That's not actually what we're going to put. We're going to take the total that it took to reach 3, which was 1, and it's taking us another 1 to reach 4. So we're going to add the total to this, right? We're not just keeping track of the single one, we're keeping track of the total path it takes for each node. We want to know how long it takes to reach node 4 all the way from our starting position. We care about the starting position. So when I put the path value, the path length for this node, I'm going to put a 2 value. So now we are once again done with this node. So now again, we are going to decide which one are we going to pop from our min heap. We want to pop the value with a shorter path. So we're going to pop this one. So now we're at this node, right? And how many nodes can this node reach? Well, it only has a single outgoing edge to this node 2, right? And we see that 2 has actually already been added to our min heap, right? But the only difference is this time, and I'm running out of space, so I'm just gonna add a little slot, is that for this 2, it's first of all, how long did it take to reach this? It took a distance of 2 to reach this 4, and plus 1 means that to reach this 2 now, it's actually a distance of 3, which is shorter than this one, right? So now we can actually add that same node 2 to our min heap, but this time we're going to have a distance of 3, which is shorter. So we visited this node, and now you can see that we only have one node remaining to visit. Good thing for us, both of our options in the min heap lead to that node. Which one are we going to pick? It's a min heap, so we're going to pick this one. 3 is less than 4, so we're going to pop this from our min heap. So now we finally popped the last node. It's a path length of 3. So now that we've reached every single node in our array, and by the way, this node does not have any outgoing edges, so we don't have to do anything more. And even though we do have a value left in our min heap, once we pop it, we're going to see that it's the same node that we've already visited. We visited this 2 node, and we visited every node now, and you can see the max value that we got in terms of length is 3. So 3 is going to be our output in this case. It takes 3 units of time or whatever for us to start at this position and then send a signal to every other node in the graph. So analyzing the time complexity of this problem is actually a little more difficult than you think. So I'm going to use E to tell us basically the number of total edges inside of our graph that we're given, and V for the total number of nodes or vertices that we're given. And just so you know, the maximum number of edges that we could possibly have is about proportional to the number of nodes squared, because like it's just kind of how it works. So like if we had 2 nodes, or rather 3 nodes, you know, we could have bidirectional edges for every pair of nodes. And if you just, basically this is just something that's true, and that's what I'm going to assume. So the max size of our heap could actually be V squared, even though we have, let's say, 4 edges. We noticed that some of the, or rather we have 4 nodes. We notice that some of the nodes could be added into the min heap multiple times. That's dependent on the total number of edges. That's why we're saying V squared is the total number of nodes that could be in the heap. So every heap operation is possibly worst case log V squared. And how many times are we going to be doing this operation? It's going to be E times worst case, basically the number of edges, because for every edge is how many times we can add values to the heap, right? So, and the way logs work, logarithms, if you take this 2, we can actually get rid of that 2, put it over here, right? Put the 2 over here, and we know how big O complexity works. We don't care about constant values. So this 2 actually goes away. So the overall big O time complexity with a priority queue for Dijikstra's algorithm is going to be E log V. This is just the general overview. Now let's get into the code. So we're actually given a list of edges, and we want to create an adjacency list of that first for Dijkstra's algorithm. So the first thing I'm going to do is create a dictionary or a hash map of
an adjacency list for these, right? So let's do def adjacency list. Pass in our, call this edges, right? Let's pass in ADJ. Let's do graph is equal to ADJ list. Pass in our times, right? Then we come here, we create our graph, right? And we do, okay, well, let's do for I in times, sorry, for node in times, then we can do graph node is equal to this, right? Let's return our graph. Let's print our graph. Unhashable list. Unhashable type list. Okay, I think it's because this is a list. Technically this node is a list, so I feel like we have to do, well, for node in range length, and then we have times, then we make it this. None is not a return type integer. Let's just like return count, make, I don't know, count is equal to 0. Okay. Then we can do, okay, well, node in I guess that's why he does do a default dic. Maybe we should do that instead. Default dictionary. Import Python. Oh, bless me, man. Oh my gosh. Oh. Um. For node in range length nums, right? For node and edges, right? Then we can go, okay, well, graph node. How would I do this? And edges. Let's do like A, B, C is equal to node, right? Graph A dot append. Can we just like append B and C or something like that? Okay, let's see how he does it.
Of
Here.
edges, initially it's just going to be an empty list. So I'm going to go through every edge in the input. So for every edge U, I'm going to get a list of all of its neighbors, right? Because we know that that's pretty useful for a Dijkstra's algorithm. We're going to basically get every single outgoing neighbor. So V is the neighbor node and W is the weight of that node. So we're going to add that to edges list for U. So this is just creating an adjacency list for us, which is going to be useful. Now I'm going to create that min heap. We want to just initialize this min heap with the first value, and the weight of it's going to be 0 because we know it doesn't cost us anything to get there, and that
U, V, W. U, V, W. Right, we return a graph. Okay, right. So now we create that min heap, like what he said, right? And we pass in our first value, right? So our V here will be whatever our K is. So I think it would be K with a weight of 0.
Starting node is given to us as K. I'm also going to have one more data structure. It's going to be a set. Basically, it's going to keep track of all the nodes that we visited because we know we don't want to go in a cycle. We don't want to go in a loop. So we do have to.
So I thought we need a visited set. It's like what we've learned. Visited is equal to set, right? This needs to be a tuple.
sort of keep track of that, I'm also going to have a variable t for the result. Initially, it's going to be 0, basically the max value that we end up getting, or the last node that we visit, and the
make that our count, right?
cost or the length to visit that node is going to be the value that we return. So now we're just going to continue our algorithm while our min heap is non-empty. We're going to keep popping from our
Okay. While min heap, okay, we pop, so we want, okay, our U and our, sorry, our, how do we do it? VW. V and our W. W is equal to, how do we pop from a min heap, dude? I have to look at the documentation. I don't
or
know.
heap while it's non-empty. We know that there's two values that we added. The weight was the first value. The second was the actual node itself. So we're going to say heap q dot heap.
Okay, he hasn't messed it up here. So we have V, which is the destination. Now W is equal to min heap q dot heap pop. Okay, heap q dot heap pop.
Pop from our min heap. This is basically
Pop from our min heap.
how you do it in Python. It's pretty easy in Python. That's what I like. And like I said, we don't want to visit a node multiple times. So if we see that this node N1 is in visit, meaning it's already been visited, then we're just going to continue to the next iteration.
Okay, so let's make this destination, because I don't like V. If dest in visited, continue.
And as you can of the loop, we don't want to go through all of this node's neighbors if it's already been visited. Otherwise, what we're going to do is add it to visit so that we don't visit it again. And we're also going to update our result t. So we're going to set it to the max of what it already is and the max of the weight that we just got. The weight is, remember, the time it.
So let's do count is equal to the max of count and the weight we just got.
Takes to reach this node. So we're going to update that. Now we're going to do the breadth first search portion of it. So we're going to go through all the neighbors of this node. So the neighbor and the neighbor's weight. So I'm just going to call that N2 and W2 because I'm bad at naming these. So in edges, basically neighbors of this N1 original node that we just popped from our min heap. We're going
to be first part, so we go, well, for des2, weight 2 in what is it, graph, in graph shit, but what is our current destination? In dest How do we input it again? Heap push, heap item, heap q dot heap push min heap, and then our item, which would be our original weight plus weight 2. Oh no, it would be a tuple, so it would be our des2 and then weight plus weight 2, I believe.
We're going to go through it, and for all of the neighbors that haven't already been visited, so if N2 is not in visit, it has not been visited yet, then we're going to add it to our min heap. So heap q dot heap push onto our min heap is going to be this node N2, but remember the first value we're adding is the weight, so weight 2. But remember, this weight 2 is just the weight that it takes for one edge, but we want to keep track of the total path length to reach this node. So we're actually going to add that W1, the first weight, to it as well. So W1 plus W2, the total path that it takes to reach N2. I know that this algorithm is actually pretty complicated. It's not a lot of code, it's about 20 lines, but it's actually, it does take some practice to get used to it. After you've written it a few times, you do kind of understand the subtleties of it. It's pretty easy to go wrong with this algorithm, but we've basically written the entire thing. So now we can return T after this loop is done executing, after the min heap is empty. Our T should give us the basically what it takes to reach every single node if it's possible, right? Remember, if it's possible, and we know that it's possible. Basically, we visited every single node if the length of visit is equal to our input value n, which tells us the total number of nodes. If we visited every node, then we can return T. Remember, the other condition was if we can't visit every single node, we return -1.
If the length of visited is equal to the length of, is equal to n, we have n, so to n else -1. There we go. Ooh. Ooh, 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 ooh.
And that is the entire algorithm. Remember, the overall time complexity total number actually came across a lot, and I'll hopefully, if this was helpful, please like and subscribe. Hope that typical actually had a lot of bugs when I was writing my code for this video, and I hope that this came across pretty clear by law.
Okay. Okay. If des2 not in visited, what is wrong here, dude? actually don't know what the bug is here. It looks correct to me. Like min heap order is wrong. My time is to be first in the heap tuple. Python's heap queue module implements heap min heap using the first element each to determine the priority. Okay. Okay. So here we need to do 0 k. We need to do wait destination for W2 and destination 2. If destination 2 not visited, then we want to do wait plus wait 2, and then our dest2. There we go. Okay. Nice. 55% acceptance on 2SOM, dude. What? What is this, dude? System design? I think I was doing Leetcode 75. Yeah, I was. Heap priority queue. How do people solve 75 problems in 1 week? Like, bro, that's insane. Like, 2,815 problems solved, bro. What? Dude, that is insane, bro. What the? 4,481 submissions in 2024. Dude, what? Bro, does this guy just Leetcode all day, dude? Like, that is insane, dude. Like, bro, this guy, like, is insane. Like, bro, this guy works full time and he solved this many problems on Leetcode. Like, bro, what? Like, dude. Impressive, dude. Let's do this one. Given a zero index array is nums1, nums2 of equal length n and a positive integer k, you must choose a subsequence of indices from nums1 of length k for chosen indices I0, I1, ik minus 1 use course defined. The sum of selected elements from nums1 multiplied with the minimum of the selected elements from nums2. We choose indices 0, 1, and 2. Bro, I'm a little confused with this. Return the maximum possible. Given a zero index, integer arrays nums1 and nums2 of equal length n. One plus 3 plus 3. 2, 1, 3. I'm a little confused with this. I don't really understand this problem. Let's take a research about this problem. 2542 maximum subsequence score. You help me understand this problem. Yeah, you know, I'm not sure about this problem. I don't know, dude. I really don't know. Oh my god, dude.
Kicking up the dirt as I pull up my skirt. When I walk by, bitch, they all on alert. Eeny, meeny, many more, you could be first.
Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem maximum subsequence score. The good news with this problem is coding it up is actually not as difficult as you would expect. Believe it or not, this is not a dynamic programming problem, and I'll tell you exactly why. But the bad news is when you see the solution, you're kind of not going to believe that it works, but I'm going to try to explain to you exactly why it does work. Now, I'm not going to show you a math proof or anything, but I'll definitely give you the intuition. So we're given two arrays that are of the same size, and we're also given a positive integer k. Basically, we want to pick k elements from each of the arrays. So suppose these are our two arrays, and let's say k in this case is 3. So let's say we pick 3 elements from the first array like this, 1, 2, 3. We can skip some elements. They don't have to be contiguous, but when we pick these 3 elements from the first array, we have to pick the same elements at the exact same index from the second array as well. So that's sort of the restriction. Now, the way they phrase this problem is they call this a subsequence, which, yeah, it kind of is a subsequence from the array, but when we take these individual values and actually use them, we're not actually building a subsequence in the output. Like from the first array, we're going to take these 3 elements and add them together. So 1 plus 3 plus 2. In subsequences, we know that the relative order of the elements does matter, but when you add elements, does the order really matter? If I add the 2 before the 3, does it matter? No, it doesn't. So just forget the word subsequence, because that's usually the word we use when we want to solve like a dynamic programming problem. But in this case, the order doesn't matter. And second, the elements we take from the second array, we want to take the minimum among all of those. So at first, this is kind of another misleading hint that this might be dynamic programming, because it's a common pattern to want to maximize the total output, which in this case is the total score, but also minimize something else. But in this case, when you actually very carefully read the problem, this is the equation that we want. We want to add the numbers from the first array, so 1 plus 3 plus 2. So this is from nums 1. And then from the second array, we want to take the minimum among all of those elements, 2, 1, 4. But we're not actually trying to minimize anything. Yes, we have to take the minimum from all of these, but we want to then multiply this by this, and we want to maximize this entire thing. Now, how do you maximize it? Well, you probably want to maximize each of the numbers in the first array, and you probably also want to maximize all of the numbers in the second array. So we don't have conflicting priorities here. Really, we're trying to be greedy. We're trying to maximize everything. So that's a bit of a hint that this is not dynamic programming. We can solve this another way, a greedy way, but it's still not very simple or intuitive on how we can do that, because there are going to be cases where we have conflicting priorities, because there are going to be cases where we have to make a choice. Let's consider a really simple example. Let's get rid of these two. What if we just had this array and let's say our k was actually 1? Well, ideally, we just want to maximize everything in the first array and maximize everything in the second array. But clearly here we have a choice. We can only choose this or we can choose this. So in the first choice, we favor having a larger N2. In the second, we favor having a larger N1. Now, in this case, the result will be, by choosing this, the result I think will be 3. With this, it would have been 2. But you can imagine how complicated making that decision would be in a very large array. How do we intelligently do that? And I'll say that basically this is a hard problem to solve. Let's try to make the problem easier for us. Let's try to actually solve a simpler problem. Let's go back to the drawing board and try to consider some brute force approaches. Yes, the simplest brute force would be to sort of have a decision tree, but that would be exponential, and you'll find that trying to add memoization to that would be difficult because there aren't really supernatural subproblems with this like array of numbers. It's hard to formulate that as a dynamic programming problem. The idea we can use is a little bit more simple. We know that in the second array, yes, we're going to take like a handful of elements, but there's only one of these elements that really matters, and that happens to be the minimum. So why not try to formulate the problem in such a way where we consider every single element as the minimum and try to find what's the maximum score we could get if 1 happened to be the minimum? Well, there's only a single 1 and we do need 3 elements. I don't think we can have less than 3 elements when we calculate a score. So in this case, we have to kind of keep adding. Well, which one would you rather add? The 2 or the 3? Well, it's kind of hard to say the way we're going through this right now because we're starting at the smallest. Why not try to be greedy like I mentioned earlier? Why not not start at the biggest and say, what if 4 is the minimum in the second array? What's the maximum score we can get then? Well, there's only a single 4, so that's not even possible. So naturally, the next question to ask would be, what's the maximum score we can get where 3 is the minimum? Why is that the natural question to ask? Because we already have a 4, and if we add a 3, we've updated our minimum to now be 3. Now, finding those elements in order is not going to be easy unless we actually sort the arrays, but we know we kind of have to keep that one-to-one mapping for elements from the first array to the second array. So what we do is create an array of pairs, but then sort the array in descending order based on the values from the second array. So when I take this and sort it, the output would look like this. So getting rid of these first two, and the output is now going to, well, the input is going to look like this. So an array of pairs, now I did draw it as 2 arrays, but we're going to have a single array. But now going back to that idea of for every single element in the second array, let's figure out what is the maximum possible score we could have where this is the minimum from the second array. We already know that it's not possible to do that for this. We just don't have enough elements with this as the value from the second array. So then we kind of expand. We have 2 elements now, and we're asking a new question. What's the max score where this is the minimum? Again, we don't have enough elements here. So then we keep going in this order now. Now we ask the question, what's the max score where 2 is the minimum? And now we finally have reached that threshold of k elements. So we can finally actually calculate a score. How are we going to do it? Well, we don't even have to keep track of the minimum, because every time we add a new element, that is going to be the minimum from the second array. So it's not like we have to take the minimum of all these k elements. That's kind of the neat part here. So our minimum is 2 from the second array. And as we go in the first array, we probably should keep a running total, a running sum of each element. That should be easy enough though. So here we would have accumulated 2 plus 3 plus 1 multiplied by 2. That's going to give us a score of 12. Now that does happen to be the result in this case, but that was too easy. This is a pretty simple example, so let's kind of continue how we would continue to solve this problem if we had a much longer array. And we haven't yet asked the question, what's the max score we could get where 1 is the minimum? Now, the problem here, of course, is that we have more than k elements. And I think this is probably the hardest part of the problem, at least in terms of the intuition, because now we have the difficult problem of making a choice. How do we make that choice? How do we know which one of these elements to remove? And I'll tell you, the answer is simpler than you might think. We know that the calculation we're trying to make is taking the sum from the first array and the minimum from the second array. So my question is, we know 1 is the minimum from the second array. So does the calculation change whether we remove 2 or remove 3 or remove 4? What I'm asking is, does the calculation of the second portion change where we take the minimum from the second array? Not really. It's still going to be 1. We're still going to be multiplying 1 by the sum from the first array. So really, it doesn't matter which one of these we choose. So we shouldn't use the value from the second array to make our decision. It's irrelevant. It's not going to affect the score. What is going to affect the score is which one of the elements we remove from nums 1, because those are the ones we're summing up. That's the main idea behind this problem. It's not simple to come up with, but now that you see it, I hope you understand it. So now here, when we are making the choice, which one do you think we should remove? Probably the 1, because it's the smallest among all of these. If we are going to be removing based on the smallest from a set of values, and we always want our set of values to be at most k, a natural data structure to use would be a min heap, and that's what I'm going to be doing in this problem. Now, before we code it up, what would be the time complexity of this approach? Well, remember, we are sorting the input array. Let's say it's of size n. That would make the time complexity of sorting n log n, and that's going to dominate the time complexity. Yes, we're going to be pushing and popping from the heap, but each operation is going to be log k because the max size of the heap is going to be k, and n operations is going to be n log n. So obviously in this case, n log n is going to be larger than n log k. And in terms of space complexity, I believe it's going to be big O of K if you don't count extra memory needed from sorting, depending on how that sorting is implemented. Now let's code this up. So like I said, the first thing we actually want to do is sort the array of pairs. We want to first build that array of pairs. Thankfully, this is pretty easy in Python. This is called list comprehension. So we're going to go through every pair of elements. And before we do that, we can actually zip the two arrays, nums1 and nums2, unpack those variables. And then for the array, we want to add a pair. I'm going to do it like this. This is actually a tuple. I guess in this case, it probably doesn't matter. You could also use like a sub list or just a tuple like I'm doing here. Then we want to sort this. So we want to do a slightly custom sorting algorithm. We want to pass in our pairs and we want to sort it based on the second value in the pairs. So we can use a lambda function. We have to specify the variable with key for sorted. That's just how this sorted method works. If you want to sort it based on some key, you have to specify that. I forgot what this is called, maybe a named parameter or something like that. But we can pass in an inline function, aka a lambda function, which will take a single parameter, which I'm going to call p for pair, and it will sort it based on the second value in that pair, so at index 1. And we also would probably want to sort this in descending order. So we're sorting this in descending order based on nums2, and then we can reassign pairs to that because I don't think this actually updates pairs. So we do have to have that line. Now to build the min heap, well, initialize the min heap, it's going to be empty. And I'm going to keep track of two variables just to make things a little bit easy. Well, one, I think we definitely have to keep track of the sum, the n1 sum. And I'm also going to keep track of the n2 minimum like this. So n1 sum is initially going to be 0. The minimum we can probably just set to float of infinity because we're trying to minimize it. Or if you don't remember how to set it to float of infinity, another valid value would probably be to just take the max from nums2, but I'm going to set it to infinity. And for now, we're going to initialize our result, aka the max score, to 0 as well. But then we're just going to start going through every pair in our list of pairs. So n1, n2, we're going to unpack these from each pair. And first thing we want to do is just update our current n1 sum using n1. And while we're at it, might as well update our n2 minimum to be n2 min or n2. But I believe since we are going through this in descending order based on n2, we really don't even need to do that. And that also tells me we probably don't even need to keep track of n2 min. n2 is literally always going to be the minimum that we've seen up until this point. So I'm just now going to clean that up. So I think this is perfectly fine to do in a real coding interview. You don't have to know exactly what you're going to do before you do it. I think it's okay to refactor on the fly. But now we know with every pair, the whole point of it is to add it to the heap queue to make sure, first of all, that we didn't go over. So first, let's update our min heap and push just n1. Remember, that's all we need to pass in. We don't even care about n2 because when we're deciding which element to remove from the heap, we only take n1 into account. So now the first thing we want to check before we try to update our score is, have we gone over the length? Has the length of this heap exceeded k? If it has, we should probably pop from that heap, and we can do that like this. So this is the n1 that we popped, so I'm going to name it slightly differently, n1 pop, and this is also the value that we want to remove from our n1 sum. So we're going to decrement our sum by the n1 pop value. Of course, I could have just moved this variable up here, but I don't think there's anything wrong with being a little bit more explicit. Now we can be sure that our heap is of valid length, but it's possible actually the heap could be less than k. The length could be less than k. So also add an if statement to check that it's exactly equal to k. And if it is, now we can start updating our result. And we know we're trying to maximize it, so we're going to take the max of the current result as well as, remember the formula is n1 sum multiplied by the minimum from n2, which we know is going to be whatever we happen to push right now anyway. And I believe that is the entire code. So now we can just go ahead and return the result out here to make sure that it works. And as you can see, yes, it does, and it's pretty efficient. If you found this helpful, please like to make sure.
I'm gonna I'm gonna delete that problem. That was a little confusing. I feel like it was a little confusing watching the video because I didn't really fully understand the question, like what I was meant to be doing. So I'm gonna come back to that later. Let's do cocoa eating bananas, man. That problem gives me PTSD, low key. Like, so let's check out cocoa eating bananas. Last time we looked at this was an extremely long time ago, man. I would have to say, yeah, November. Yeah, really long time ago. Nearly 6 months ago. I had a lot of trouble with this problem visualizing it. We're going to try to relook at it. We have about half an hour left. I don't know how long we've been going, but about an hour and 40 minutes. Jeez, okay. I didn't realize it was that long, but so we'll do this problem for about 20 minutes, and then we'll call it if I can't do it. Coco loves eating bananas. There are n piles of bananas. The ith pile has piles I bananas. The guards have gone and will come back in H hours. Coco can decide her bananas per hour eating speed of K. Each hour she chooses some pile of bananas and eats K bananas from that pile. Each hour she chooses some pile of bananas and eats K bananas from that pile. If the pile has less than K bananas, she eats all of them instead and will not eat any more bananas during this hour. Coco likes to eat slowly but still wants to finish eating all the bananas before the guards return. Okay, so H is our banana eating speed. No. Okay, H is equal to 8, right? So H, turn the minimum integer K such that she can eat all the bananas within H hours. She chooses some random pile, right? That's how we know it's binary search. And eats K bananas from that pile. Coco likes to eat slowly, but still wants to finish eating all the bananas before the guards return. Okay, but she chooses some pile of bananas and eats K bananas from that pile. So we're given how long the guards are gone for. Okay, so we're finding the speed. Return the minimum integer K such that she can eat all bananas within H hours. So the guards are gone for 8 hours. Okay, I didn't know you could edit it like that, but alright. That's cool. Okay, so we're looking for I think the minimum speed. Return the minimum integer K such that she can eat all bananas within H hours. So they've gone 8 hours. Right, so low is equal to 0, high is equal to the length of piles minus 1, right? So while low is less than or equal to high, so while low is less than high, right, we calculate our mid, right? We'll loop through, start here. Oh my gosh, dude, what did I just do? Or what the hell? Okay. Okay, so instead of doing it on these bounds, I think we have to actually do it on the max here. The max speed would have to be 11, right? So be the max of piles, right? So while low is greater than high, what? While low is less than high, we want to calculate our midpoint, right? So is it always going to be mid is equal to high minus high plus low divided by 2, right? Okay. Floor high plus low over 2. Oh my gosh, dude, this is so annoying. Guess this is our eating speed, right? Technically. Okay, so if we do, well, calculate our eating speed. Now, whoa. Dude. Might freaking die, dude. While low is less than high, k is equal to high plus low over 2. So now what do we want to do? We want to we would just want to loop through, so really probably what we want to do is we probably want to add all these numbers up, right? So for I in range, for I in piles, for ban in piles, okay, we can do, well, total bananas, chicken, banana, total bananas is equal to plus or equal to ban. Set this as 0. Okay, total bananas plus or equal to ban, right? Okay, so we go through, we get that. So now we would probably want to divide k by if k total bananas divide by k I don't know how I would do this. Bananas divide by k is less than or equal to h, then probably want to try something smaller as well. So we would go, okay, well, we do low is equal to low minus 1, but res is equal to res is equal to k. Right, we do our right. Right, is equal to k minus 1. Else, right, this would be less than, right? If it's greater than, then we'd want to do, well, left is equal to k plus 1, right? And then we'd probably want to return res. Okay, we got some sort of infinite loop here. Okay, left, right, right, left. Okay, so here we're actually doing so this is wrong. So they sum the hours. They do hours equal to sum math.ceil ben over k for ben in piles. So as we loop through each pile, we're dividing it by k, and we're taking the ceil of that. And then the sum of all of it. If hours are less than or equal to k, we move, else this. That good now? High is not defined. Did you mean right? I did mean right. How did you know? Low is not defined. Oops, while left is less than right. There we go. Nope. Got a 47 or a 46. I think we need this. There we go. Okay. I appreciate you guys watching the video today. And I'll see you guys tomorrow. See you guys later.